Let's look at the addition of HBr to an alkene, and you'll notice that the particular alkene I've chosen for this example has a chiral center in it. That'll become important later. But for now, we're just going to focus on the double bond. And we know that when we add HBr to an alkene, we want to think of this as being H plus and Br minus. And we know that the electrons in this double bond react with that H plus. When this happens, the hydrogen ends up on the terminal carbon because we're going to want to get the more substituted carbocation. And in this more substituted carbocation, you can see the positive charges near my phenyl group. And sometimes we have to worry about rearrangements with carbocations, not in this particular case because conjugation with the phenyl group will help stabilize that. I want to look at the three-dimensional structure of this carbocation because there are a couple of important things I want to point out to you. First, you'll notice in my three-dimensional model I've shown the p orbitals that make up my pi bond in my reactant. And I've represented the phenyl group with this green sphere, and I've color-coded the methyl red and the ethyl group blue. And the first thing to keep in mind is that the H plus that gets attacked can react with either side of this p orbital. It can come in from the top, it can come in from the bottom. Since there are two other hydrogens here, it doesn't really matter in this case, but if there were different groups here, it might affect things. Now you might be able to argue that since this methyl group is blocking the top a little bit more than the bottom, it'll probably come in from the bottom, but that's not really important for us right at this moment. What I do want to look at is the carbocation that results when this attack of this carbon by the hydrogen happens. So in this model we have our hydrogen that has added to the end carbon here. It's on there now. And we have a carbocation now, and keep in mind that the carbocation is planar, it's flat. You can look at it, you can see that it's flat. And it still has an empty p orbital, or now has an empty p orbital. And it's this carbocation that the Br minus is going to react with, and I can show that over here with my arrows, with this bromine coming into this carbocation. I can do the same thing over on this three-dimensional model. I can show the bromine attacking. And what I want you to notice is that just as with the hydrogen, which could attack either side, the Br minus can come into this molecule from either side. It can come in from above the plane, the way I have it drawn, or it can come in from below the plane. And depending on which side it comes in on, we get different products. The same connectivity, but different orientation space. In other words, different stereoisomers, depending on top attack versus bottom attack. And this is what I've shown here. On the left-hand side, the Br has come in from the top face of the carbocation. And on this product over here, the Br has come in from the bottom face of that carbocation. Let's look at the products on the other side in the two-dimensional drawings. And what I do want you to notice is that on this carbon right here where my bromine has come in, I have 4 different groups coming off of it. I've got the phenyl ring, I've got the bromine, I've got this methyl group, and I've got this hydrocarbon chain. It's 4 different groups. I've made a new stereocenter. If I look over here, the one where it has come in from the bottom, my new stereocenter is R. On the other hand, the one where it came in from the top, and this is actually labeled wrong, it should say that this is S, and I've changed that. So a new R stereocenter or a new S stereocenter. I want you to remember we started with a stereocenter in our molecule, and that stereocenter doesn't change through the course of the reaction. That original stereocenter was S, so our 2 stereoisomers we made, one is the SR isomer, one is the SS isomer. What is the relationship between these 2 isomers? They're not enantiomers because in order for them to be enantiomers, they'd have to be mirror images. This would have to be RR and SS, or SR and RS. So if they're not enantiomers, they must be diastereomers. Stereoisomers that are not mirror images of one another are diastereomers.